Hello and welcome. We are continuing our practice of our combined gas law problems. So last time I showed you a problem that involved the combined gas law up here. Now we're going to move on to another problem. Don't know which equation we're going to use yet until we figure out what variables we have. So this problem says that a gas has a temperature of 15 degrees Celsius, that looks important, and is at 670 torr. That sounds useful. If the pressure changes, oh, there's that word again, tells me I'm using the combined gas law or one of its cousins. There's a new temperature, and what is the new pressure? So to translate these all into variables that are more familiar, temperature, pressure, and pressure. Remember, temperature is the unit that you do not get a say on. It must always be done in Kelvin. So we add 273. Oops. Now my pressure unit here, my problem does not specify a particular unit, so you can leave it in torr if you like. Just to demonstrate, this is going to make use of Gay-Lussac's law. Excuse me, I had to think there for a second. But I want to show you how we can use the combined gas law to take up a little less space in your brain. So this problem says nothing about volume. So since they said nothing, we're assuming that volume stays constant. That means volume does not play a role in my equations, and I can just cross it out. That leaves me with the simplified, and there's Gay-Lussac's law, without me having to pull that specific law out of my brain. We're looking for P2 here, so let's get that variable by itself. T2 is being divided. That means I'm going to have to multiply both sides by T2. It's the beauty of algebra. You can do anything you want to one side of the equation, so long as you do the same thing to the other. So now all we have to do is just plug in our numbers. So 670 times 298 divided by T1 is 288. How many sig figs can I have? Looks like 2, so no more than 3. Oops. What unit am I in? Torr. This should make sense with regards to the kinetic molecular theory. Because my temperature has increased, my particles are moving around a lot more. My volume has not changed to give those particles more room to move. So that means that they have increased the pressure. They're running into the walls more often. I have time for another one? Yeah. Let's see, what one shall we look at next? Just to look at this problem really quick, we have a temperature and a volume that changes. So this, again, looking at our combined law, temperature, volume, what is new temperature? Pressure is not mentioned. We can take it out. There's Charles's law. So you can use this combined gas law to simplify into any of the equations that you need. But look at number 4. Now all of a sudden I have an amount in there. That's kind of strange. 37 grams of carbon dioxide, so it gives me an amount at, we've got 150 Kelvin. There's my temperature. We have a pressure and a volume. My goodness, they told us all kinds of stuff about this one. Its environment changes. There's that word again. So these are all the initials, and then I'm going to have a final situation. Now, since we're looking at things that change, notice my moles, my amount did not change. That means it does not apply to this problem. It does not matter. So all 3 variables are present. It's another situation. for that P1 V1 over T1 equals P2 V2 over T2. I trust you can do the math by now, so I'm going to move on in the interest of not taking up too many videos. One more problem before we call it a day on this section. This guy up here, 12.3 grams of hydrogen has a volume of 19 liters. Well, that sounds useful. .3 grams of helium is added. Oh, so we did something different. Something changed. So that means I'm going to have an N1 and an N2 again, V1 and V2. We don't know what V2 is. That's what they're asking me for. And we said N has to be in moles. So let's go ahead and convert this guy to moles real quick. So we've got 12.3 divided by 2.02. Moles of hydrogen, but think about your initial situation. If I start off with a box that contains hydrogen at a particular volume, then I add helium, now what's inside my box? I didn't take the hydrogen out, so it's there as well. So we're going to have to add together the amount of hydrogen and the amount of helium. So we already found moles of hydrogen, can't add apples and oranges, so I'm going to have to convert helium to moles as well. Helium's formula mass is 4.00. Can you see that up there? Yes, you can. So 12.3 divided by 4 is 3.075. So that means N2 is going to be the sum of my two gases. So 6.089 plus 3.075. So this is my total moles in my second scenario. So always be careful to think about what is actually happening in the before and in the after. This uses only N and V, so we're talking about Avogadro's law. As I said before, you can do anything to one side as long as you do it to the other. So if you put the N on the top, N1 over V1 equals N2 over V2, we just flip them both. And we can deal with the reciprocals. I'm looking for V2. To get N2 away, it's divided here, means we have to multiply both sides. Leaves me with V1 times N2 divided by N1 equals V2. So let's see, V1 was 19 times N2 was 9.164 divided by N1 was 6.089. How many sig figs can I have? Looks like 2, so no more than 3. Since this unit was liters, so is this one. And stop and think. That should make sense. I added more gas particles to my box. My pressure was kept constant, as was my temperature, since they're not mentioned here. Means the size of my box must enlarge to accommodate, to accommodate this larger amount of my gas particles bouncing around. So things to be careful of in these problems. First off, watch out for your units. Whenever you're dealing with a situation that changes, your units must be consistent for both P1 and P2 or for V1 and V2. However, temperature must always be in Kelvin. Just add 273 to your degrees Celsius to get your amount in Kelvin. N always represents moles. So get in the habit of any time you see a problem dealing with pressures and temperatures and all that jazz, if you see an amount, convert it to moles. If you see a temperature, convert it to Kelvin, especially the temperature one. Just do not stop, do not pass go, convert to Kelvin. The end. The next video will introduce the ideal gas law along with a couple of examples. From there, we'll move on to gas law stoic. So now we get into the slightly more complicated stuff. See you there.